Good. Yeah, good afternoon, everyone. So I'm probably the least knowledgeable person about blockchain in the room. So I, on purpose, left any blockchain comment and reflection out of my presentation. My goal today is to cover CubeSats and what they are, what they can do, what we do with them, what we build. The only blockchain reference was my working title was ICO, as in initial CubeSat offering. That's going to be the only blockchain joke, I promised. So who we are? So we are ISIS, the other one. You probably know our after-sales department in Syria, and we recently closed the Baghdad office. So we've been around, Innovative Solution in Space, we've been around since 2006. We're based in the Netherlands, between The Hague and Rotterdam. The company started as a spin-off of the Delphi C3 satellite project from the Technical University of Delft. So 5 guys who worked on this project as students and launched the satellite, decided they did a good job, and building the satellite that is still working now. So 10 years in orbit. They started the company a bit before the satellite was launched. 10 years in orbit, still working. And so they decided that they wanted to continue in this business and sell subsystems to other universities that are also building satellites. And that's how the business started. Building structures, communication systems, onboard computers for other universities to use. Then they also realized that it was difficult to launch satellites, and getting in contact with the launch providers and putting your stuff on rocket is not easy. There are technical challenges, but it's also a lot of relationship building that you have to do, and understanding the launch world. And also when they started in this business, CubeSats were really new. So these small satellites, so approaching launch providers to be able to get your satellite on a rocket was difficult. So we started as one of the first launch brokers for CubeSat. So basically what we do is we buy extra capacities on rocket next to big satellites, and then we resell that to our customers. And those are the 260 satellites that we've launched. So we haven't built all of them, but so they are satellites that we've launched through this launch brokering service. And we've done that over 13 launch campaigns all around the world, and we have a bunch of these coming still this year, and many opportunities in the future as well. So 12 years in, we are now about 90 employees. Most of us are in Delft, in the Netherlands. We also have a small office in South Africa, and we're also interested in opening more offices around the world. I'll explain the business as I go through the presentation as well, but we do build satellites, including the subsystems. We also do the system integration. We launch them, as I said, and we also operate them from our ground station in Delft. And the satellite that we're involved with are typically between 1 kilogram and 25 kilograms, so really small. I wasn't exactly sure of the level of knowledge of the audience about satellites, so I'm going through a few different concepts that we deal with. Maybe it's very obvious. I think there's still coffee outside, so feel free to get out for the next few slides if that's too obvious and too easy. But our main role now as a company and what we do is, so we are a turnkey mission provider of CubeSat in low Earth orbit. And I will just go through the different concepts, starting by the end, with the low Earth orbit. So most of the satellites that people usually think of are big geostationary communication satellites. So GEO is geostationary orbit, an orbit at an altitude at which the period of the orbit is roughly 24 hours. So the satellite will go around its orbit at the same rate that the Earth is rotating on itself, so it always stay over the same point. That's not the orbit we're in. We are in LEO, which is low Earth orbit, where you typically have the ISS, you have Earth observation satellites that are there, and most of the CubeSat that were launched and that are operating there. It takes much less energy to go to LEO than to go to GEO or even beyond. Although last month we've been to the moon. So we've built a hosted payload. It's not a complete satellite. There are subsystems that we have built and that we've mounted on a Chinese probe that has been launched to the moon last month. And so we are doing science operations from that location. Same subsystems that we have in our CubeSat. So that's just proving that for now we are in low Earth orbit, but we have much bigger ambition than that, and the moon is one of them. So that was for the low Earth orbit. Now what we mean by turnkey missions, so the satellite of course is only one part of the overall system, of the mission. So that's what we call also the space segment. But you also have the ground segment. You need to have the ground stations, the antenna and the radios to actually receive the satellite and the data from the satellite and communicate with it. And so the operation side also linked to that. You need to get the satellite to orbit as well. So you have the launch segment. It's big in this picture, not only because I had to feed the rocket, but also because that's a big chunk of your budget that will go there. And once you get all that money from the VC, that's typically where you will have to invest it as well. There are also byproducts of the mission, so training and support. We use a lot of these satellites for knowledge transfer and capacity buildings for countries or entities who don't have a lot of experience with space, and we can also train them and support them as part of this mission. And then all the new developments, so all the things specific to the mission or new technology that we have to develop to enable certain mission. And we can do all of that basically. So in some cases, we will just provide part of the satellite, just the subsystems like the company started. In some cases, we will just provide the launch, but we can also, and we also have customers coming to us with a need for data or a certain service or an instrument that they would like to fly, and then they don't want to take care of any of the other satellite business, and then we can do that for them. And we can also do what we call in-orbit delivery. So we build the satellite, we launch it, we commission it, so we make sure that it's working properly in orbit, and then we hand it over to the customer for operation. Or we continue ourselves with the operations. So that's what we mean by turnkey. As part of the satellite itself, so I'll typically talk about bus or platform on the one hand and payload on the other hand. So the payload is the reason why you launch your satellite. It's your instrument. It's your camera, your sensors, your radio system if you have a communication satellite. Whatever reason you launch the satellite for, basically. What you want to have in space. And the bus and the platform is what's going to support the payload. So power management and data management on the satellite, communication with the ground for housekeeping data and this kind of thing. So that's all the boring stuff that can be common from one mission to the other, but that you need in order to support the payload in orbit. And that's the part that we are focusing on. So we have developed a bunch of payloads. We can also have access to payloads in order to provide the right data to our customers. But our core business is really in the bus and the platform, and we will work with partners for the payload. So that's the turnkey mission part and the low Earth orbit part covered. So now I can focus finally on the CubeSat and on this crash course. So here's one, for instance. So very small satellites. So this one is a satellite that we've launched last year. It was a technology demonstration. Dimension of the system, 30 by 10 by 10 centimeters. So a bottle of milk, typically. So very small. The mass was around 4 kilograms. And that's one of the many sizes that we can have as far as CubeSats are concerned. So the whole family that we are working with, we talk in terms of U or units. So one unit is 10 by 10 by 10 centimeters, a small cube with a mass typically between 1 and 2 kilograms. And that's the origin of the CubeSat. So that's something that was developed by Cal Poly and Stanford in the US in the late 90s. And the idea was to develop a new standard of satellite to force the students to think inside the box for once. and force them to comply to certain standards and certain constraints in order to facilitate the development and then the launch. Because all the interfaces, the general design of it, and then the interfaces to the launch vehicle will be standardized. So it started as this really, really small satellite. Smaller is also cheaper to launch. But then as the concept developed and people wanted to do more interesting things with them, they also realized that this was very constraining. So we've seen the evolution of the spacecraft, the PC revolution, from the very big satellites down to the smaller and smaller and smaller ones. Now we're also seeing the other effect. And something that I usually say is, yeah, the PCs started very big with a big mainframe that takes a whole room and got smaller and smaller up to the point where we have small laptops and phones. But if you look at the phones themselves, cell phones started really small, and now they're getting bigger and bigger and bigger because you want a bigger screen. And we see something similar with CubeSat. So they started at this 1U, 10 by 10 by 10 centimeters, around 1 kilograms. But then they have also grown during the years. And so now most of the satellites that we are building are the ones that are in the middle of this slide, so 3Us and 6Us, and we are working with bigger satellites as well. The advantage is, as you can see in the upper right, so that's a 3U CubeSat with deployable solar panels. Because I'll mention it a bit later, power is a big issue. You need to generate power for your payload, for your instrument. Deploying more complex solar panels is one way to do it. Having a satellite that is a bit bigger with cells that are on the satellite is another way to do it, for instance. You also get more volume inside. So CubeSats are not only these really, really small satellites. There is a wide range. There is the whole family. So then a question that I get a lot is, well, how do you launch them? Well, we use what we call deployers or dispensers. So you have an example here, big blue blocks. The principle is very simple. So you can see a bit the springs inside. So you have a plate and then a spring behind it. And as you see the picture on the left, you will slide the CubeSat inside this dispenser. Then you close the door. You bolt that on a rocket. Then there's a big boom in the right direction. And once you're in orbit, open the door, and then the spring will simply push the satellite outside of the box, and it's in orbit. And the nice thing about that is that the only thing that we deliver to a launch provider is a closed box. So they don't have to care about what's inside the box. Well, there are a few legal details, but as far as the technical issues are concerned, what's in the box is the responsibility of the satellite builder. The launch provider just sees a blue box with a certain mass, and that's what's mounted on the rocket, and that's what they see. And so if it's a telecommunication satellite built by a private company inside, or if it's something very new that was bolted together by a bunch of students from I don't know what universities, to the launch provider is technically it's the same. So that's the advantage that we have, and that's also how we can have this good relationship with the launch provider and launch so many of these satellites, because we have simplified the interfaces on either side, to the customer, to the satellite provider, and to the launch provider. So that's how we put them in orbit. Second thing I want to talk about, last thing I want to talk about what are CubeSat is the philosophy that is behind it. So the nice thing with this system is that they can be very, very modular. So you have seen the different sizes, and the way we build them is by using the same building blocks, whether we're talking about a small satellite or a big one. We get more performance out of it, we get more power or processing power, we have more volume, but the general idea is the same. And if you're talking about the really small 1U CubeSat or the much bigger one, we will have typically the same kind of onboard computers. So you can see our onboard computer on the picture. And then the idea is to have these Lego blocks. So we'll have the onboard computer that is connected to the power system and to the other systems on the satellite. And we can expand the performance. But the blocks themselves, they stay the same. So we can also mass produce these systems, and so we also gain on cost on the one hand. And the the other difference in philosophy between these small satellites, between CubeSats and the larger satellites, is also the type of components that we use and the level of risk that we take. So we typically use off-the-shelf electronics components. We don't use red hot components. We do a bit of screening of the electronic components that we do, but not as much as that is typically the norm in the space industry. And the advantage is that we have access to the components much quicker than what the traditional space organization do. And we can also reduce the cost like this, because red hot components and space proven components or qualified components are more expensive than the off-the-shelf electronics. So we can reuse the same subsystems no matter what the size of the satellite is. We typically don't have custom-built subsystems per mission, and we use commercial off-the-shelf components. So we reduce the cost like this. I'll talk about the implication of that a bit later. But now that's the time of the presentation when I disappoint you, because we hear all these great things about CubeSat and how small they are and how fast they are and how they are going to completely change the world and do things. As in most things in life, it comes at a certain cost, and they do have limitations. And one of them, so I mentioned briefly, is the power generation. So we have so many people coming to us with this great idea and this great payload and all this processing power that they need and that they would like to fit in the CubeSat because they've heard that they're cheap. We discussed about going around laws before. There are some laws that we can't go around it, and those are the laws of physics. And if you want to have power in your satellite, then you will have to put solar cells on them. And you have an example here of a 6U satellite that we're working on with deployable solar panels. You will generate roughly 100 watts peak power. So that's when the cells are pointing directly at the sun. Of course, in low Earth orbit, you also have period of eclipse. You have the Earth, which is in between your satellite and the sun. You don't generate any power. You have to rely on your battery at this time. And then, depending on how the solar panels are pointed at the sun, you will generate more or less power. So, on average, you actually have 30 to 60 watts directly available from the solar panels. So you have to rely on your batteries then if you need to have more power during that amount of time. So you will deplete your battery that you will then have to recharge as well. So that's one of the limitations. The other one is the obvious one. That's the volume that you have available. So they can do a lot of things, but as I say, it comes at a cost. And it doesn't mean that they are smaller and cheaper, but they can do the same as what big satellites can do, because there are things that we can't change. Another big limitation that is probably relevant to you as well is the data rate that you can have. So that's the ground station that we have in Delft. So it operates on a UHF and VHF for uplink and downlink. That's what we use to send simple commands to the satellite and receive the housekeeping data. And then we have a dish as well for S-band. And so we also have a version with a larger dish for better performance, for slightly higher data rates. And we're working on an X-band station as well. But typically the rates that you get is around 10 kilobits per second for UHF, 10 megabits per second for S-band, and 100 megabits per second for X-band. But that's basically what you will get. And the satellite is moving pretty fast. As I said, in LEO, you have an orbital period of around 90 minutes. So the satellite is going fast, and is not going to stay overhead for very long. The orbit is as well what the orbit relative to the Earth is also moving, because the Earth is spinning. So you typically have in LEO 6 passes a day. So that's 3 during the day, 3 during the night, and on average about 7 minutes each. So that's it. That's not a lot of time that you have with your satellite, and the data rates are still pretty low. Of course, that's just for one ground station. If you have a ground station network, and that's one way to improve the situation, then you can increase the data volume that you get. But this 100 megabits per second, that's pretty much the state of the art now. So there are systems. Some of them have been launched. Prototypes have been used that can do much more. But that's basically the situation right now. And that's mostly due to the power that you have available on board to transform into RF power. But that's also due to the size of the satellite, because you can have only small antennas, so you don't have a lot of gain. So you can't have rates that are really high. And that's something that you will have to take into account when looking at these CubeSats. Yes, they have benefits, they have advantages, but it also come at a cost, and that needs to be taken into account. But now I'll talk about the good aspects again. And one of them is the short development time. And as I said, that's due to two reasons. The first one is the fact that we use off-the-shelf components, so we can have access to them relatively quickly. And the other one is the level of risk that we can take. And then the standardized building blocks, meaning that if we build an Earth observation satellite or a communication satellite or another type, the platform, the bus, is going to be pretty much the same every time. So we also spend less time designing and refining, and we can reuse not only components off the shelf, but also design that are almost on the shelf as well. And the risk that we take, it's not only in the selection of the components, it's also in the level of testing that we're going to do. And then that all depends on the customer and also on the amount of risk that they want to take. If we work with the European Space Agency, we're typically going to spend much more time testing the satellite and refining. And we know how to design satellites like this. Of course, it's not the same price and it doesn't take the same time. Typical timeline from the kickoff meeting, signing the contract, all the way to launch is typically 12 to 18 months. We've been much faster than that once, and ideally we don't want to do it again because that's obviously very stressful, but the main reason is the amount of risk that we took. So the two satellites that you have on the picture here, they are the two precursors for the QB50 Constellation, which was a research project funded by the European Commission. The idea was to launch 50 satellites, hence the name. In the end, only about 38, I think, of these satellites were launched, all built by different universities, different entities, and they're working together to take measurements in the upper atmospheres. The European Commission wanted to de-risk the project a bit and test the payload and test some of the components that were going to be used. So we built those two satellites, and from kickoff to launch, there were only 4 months to build two satellites in which we had a completely new onboard computer, a completely new revision of the radio system that we were using, two payloads that we had never worked before. I showed you the blue box, the deployer that we used for the launch. That was the maiden flight for this version of it, which is much bigger, and that was completely new. Because we had not only these satellites, but we had all other customers on this rocket. We also had 5 of these dispensers with paying customers inside. And we realized that the launch vehicle didn't have enough data and power interfaces to interface with 5 boxes. So we also had to develop on the spot a sequencer to be able to receive the signal from the rocket and then distribute that to all the deployers. So as I said, we can do it. We loved doing it, but we'd rather take a slightly more conservative approach in general, and not only for us, but also because, as you can imagine, although it was supposed to be a de-risking mission, we actually took quite a lot of risk. And one of the additional things that we did during this mission, because of the time constraint, both satellites were actually launched with very limited software on board. And then we had to spend our time develop a way to reprogram the onboard computers in orbit. And we've done that multiple times since. And so that's also something that we are able to do now, and we learned a lot from this mission. And that allowed our software engineers to focus only on the core functionalities first, and then this bootloader, this way of updating the firmware of the satellite on orbit. And then they had much more time between the time when we delivered the satellite for launch and when it was actually launched to continue the software development, continue testing, and then upload the software afterwards.
So did it work?
They did work, yes. So one of them is still in operation and still working fully. The other one accomplish all the mission objectives. And then we had one failure on board where one of the radios stopped working. And we think it's due to EMI, so electromagnetic interferences between one of the payload and the radio system. And that's a great question because that's exactly what you get when you don't test enough. So that's typically the level of risk that you take. So one is still working, the other one worked for the mission that was planned, and then we had this one corner case where the satellite failed. So short development time, first big benefit, and the second big benefit is the lower cost. Again, because of these standard components and standard building blocks. So that also means that for the price of one big satellite, so that's an Iridium Next satellite that operates in LEO, you can launch a lot of these CubeSats. And that's including not only the cost of the satellite, but also of the launch. And then you can use them together in a constellation with many additional benefits. So in terms of revisit times, so you have more satellites going over the same spot over the Earth. So you also increase your coverage. Scalability, meaning that you can launch a few satellites, you have a small constellation giving you a certain level of performance, and you can add satellites to this, you have the same basic service, but you improve the accuracy that you get, or the coverage, and then you generate more revenue as you add satellites. Failure tolerance, so basically that's what we call external redundancy. So we typically have limited level of redundancy inside the satellites, but then if you have another exactly the same satellite just next to it, if one fails, you still have the other one. And low data latency, because if you have the constellation in orbit and the ground station network, you can also basically download data more often from the satellite and receive the data more often. You can also use inter-satellite link, and the satellites will communicate to each other and then retransmit the data until there is one satellite that is in view of a ground station. Do I still have a bit of time, or 2 minutes? Okay. I'm almost done. I'll go then quickly over a few of the applications of what they can do. So we've heard about many of these applications. So I'm not going to spend too much time on this slide. I'll just talk about two specific examples. One is Planet, formerly known as Planet Labs. I'm not going to take any credit for the satellite themselves. We don't build them, but we do launch them. So they operate around 300 satellites now, and the mission objective is to take a picture of the whole Earth every day. So they have all these satellites around taking picture of the Earth with very good resolution. And they were one of the very first VC-backed companies who actually launched their constellation. And the other one is two satellites, 2 6U that we are building now that we will launch in August for a company called Hyber in the Netherlands. And so they basically have a machine-to-machine system. Their idea is to have a constellation of satellites listening to sensors on the ground. And one of the applications, for instance, would be container tracking and asset tracking on the ground that can be used for agricultural improvement as well. It's up to their end customer actually to decide what they want to do with the system and with the data, and we provide the satellite to them. This one, as I said, I'm not going to talk about, but I'd be happy to hear your thought about it and how we can integrate blockchain in our system or help you launch your own mission. Thank you.